Rồi, sẵn sàng.
Xin chào mọi người, quay trở lại với section 2 của hội nghị gặp gỡ mùa hè năm 2021. Tôi rất là vinh hạnh được giới thiệu giáo sư Nguyễn Thị Hoàng Oanh. Thực ra là hiện nay đang là giáo sư ở Đại học Brown rồi, nhưng mà UIUC là thông tin cũ thôi. Rất trân trọng được giới thiệu giáo sư Oanh, sẽ báo cáo cho ngày hôm nay thì để giới thiệu rất ngắn về giáo sư Oanh để các bạn được thấy là con đường đi của giáo sư Oanh như thế nào. Thì Oanh là học đại học ở lớp cử nhân tài năng khoa toán tin học của trường Đại học Khoa học Tự nhiên, và tôi là rất may mắn đã từng được dạy bài tập cho giáo sư Oanh trước khi qua Mỹ. Và sau đấy là cả cuộc đời của giáo sư Oanh ở Mỹ là hầu như là ở Ivy League. Đó là giáo sư Oanh học tiến sĩ ở Đại học Yale với giáo sư Vũ Hà Văn, làm postdoc ở Princeton, và chỉ có 1 năm ở UIUC thôi, và bây giờ lại quay trở lại Ivy League ở Brown. Và xin mời giáo sư Anh báo cáo về From the Classical CLT to the Universality of Random Polynomials.
Dạ, em cảm ơn anh Hân đã giới thiệu. Em cảm ơn mấy anh đã mời em để give talk ở cái buổi hôm nay. Thực ra là lần đầu tiên là em give talk ở gặp gỡ mùa hè. Vậy có cái hồi trước đó là lúc em sinh viên thì là em tham dự thôi. Sau đó thì cũng không có dịp về Sài Gòn. Em có về nhưng mà cũng không có ở Sài Gòn, cho nên là cũng không có dịp tham gia gặp gỡ mùa hè này lần đầu tiên. Thực ra thì bây giờ officially thì em vẫn đang ở UIUC. Nói thì nó cũng hơi khó nói bằng tiếng Việt, cho nên là em xin phép là em cái talk này thì em nói bằng tiếng Anh. Thì em sẽ cố gắng là nói đơn giản thôi, nhưng mà nếu như mà mọi người có câu hỏi gì thì mọi người đừng có ngại hỏi nha, hỏi bằng tiếng Việt cũng được. So today we're gonna talk about the classical central limit theorem and the relationship between it and the universality for random polynomials. What is so universality is the main one of the main research direction that I have been doing in the past few years. So let me start with the very classical central limit theorem that possibly most of you have seen it before. So it says something like this: if we have C1, C2 up to Cn are independent and identically distributed random variables with mean mu and variance sigma square, then if we look at the distribution of the sum, and what we do is we what happened with this sum, the sum as I runs from 1 to n, it is a random variable with mean, what is just a sum of the means, so will be n mu, because each of this guy has mean mu, so n of them, the mean is n mu, and the variance, because these are independent, so the variance is just the sum of the variances. So the variance of this sum is going to be n times the individual variance, which is sigma square. And in other words, the standard deviation is going to be the square root of the variance, which is square root n times sigma. Now, the central limit theorem says that if you look at the sum and subtract the mean, so that we have a random variable with mean 0 and divided by the standard deviation, by that it's just a very standard normalization to make this random variable normalized, meaning it has mean 0 and variance 1. For some reason, I'm hearing my own echo. Anyway, so this one will converge in distribution to standard Gaussian. Now, if you don't know what convergence in distribution means, that's fine. I'll talk about it quickly. Now, what is the standard Gaussian, also denoted by N01? It's just the what we normally call the bell curve. Now, why is it called universality? This is actually one of the simplest form of the universality phenomenon. And what it say is, meaning roughly speaking, the universality phenomenon says that if you are interested in certain object, for example, in this case is the sum of a large number of things. In this case, it's just a sum of a large number of random variables. Then most of the time, then the central limit theorem says that this sum has the universality property, meaning it depends very little on the distribution of each of these individual guys. And it says that if you normalize it properly like this, so just so you make it a random variable would mean 0 and variance 1, then the distribution of the object that you are looking at is universal. So it is roughly standard Gaussian. It does not depend on whether you start with the CI being, Bernoulli, for example, plus minus 1 random variable, or you start with the CI being uniformly distributed in the interval 0, 1, for example. It doesn't matter what distribution you start with. The sum, the distribution of the sum in the limit is universal. So that's basically the idea of the universality, and the central limit theorem is perhaps one of the simplest. And so let me start with the proof of the classical central limit theorem. It has actually a lot of proofs, and here I'll just mention one of them. It is known as the Lindeberg swapping method. And let me just start by talking a little bit about the convergence in distribution first. So a sequence of random variables Zn is said to converge in distribution to a random variable Z, if and only if for every smooth functions f with bounded derivatives, then we have expectation f of Zn converges to expectation f of Z. So this is just a real number, and this is another real number. So we have a sequence of real number that converges to another real number in the usual sense that we are familiar with. If this happens for every smooth function f with bounded derivatives, then we say that Zn converges in distribution to Z. So this is what an equivalent definition that we're going to use. But originally, what it means for Zn converge to Z in distribution in the sense of the central limit theorem, for example, it just means that the law, so the probability that Zn is smaller than A converges to probability that Z smaller than A for every A. In this case, when Z is the standard Gaussian. When it's not standard Gaussian, but it's discrete, the definition is slightly different. But this is what it means. And so it basically say that the distribution of Zn converges to the distribution of Z. All right, so we are going to try to prove something like this. So we fix a smooth test function and we try to prove the convergence of the expectation. And now, before we do that, some simplification.
Oanh ơi, xin lỗi cho anh dừng một chút, là có câu hỏi của bạn Minh Nguyễn là cho hỏi là cái convergence in distributions này nó là convergence in D hay là D phẩy?
D phẩy là gì?
Bạn Minh Nguyễn có thể nói được không ạ? Để đặt câu hỏi cho nó rõ.
Thì cái random variable chị có thể xem như là một cái cái distribution theo nghĩa SWOT thì conversion in D conversion in D prime chị apply một cái test function thì em thấy cái smooth f with bounded derivative is something similar to a test function. Thì trong cái lý thuyết về cái distribution này có hai loại conversion in D prime và conversion in total variation. Thì tại em không có hiểu, em chưa có hiểu được là cái y này nó cái expectation nó tương đương với cái gì, nghĩa là chị có thấy chị có lấy giá trị absolute value của hàm f này không? Nếu mà chị lấy cái absolute value thì nó là total variation.
Chị không có lấy absolute value, mình cái này là expectation này thì tức là mỗi cái random variable thì nó sẽ associate với một cái distribution mu, đúng không? Thì cái expectation này nó là tích phân của f x d mu x.
Giờ cái này là cái conversion in D prime.
Chị không có nhớ rõ mấy cái D với D prime ở đâu á, cũng không dùng cho nên cũng không nhớ, nhưng mà cái này là như vậy.
Dạ vâng, dạ em cảm ơn.
So going back to the simplification, these are pretty standard actually. So firstly, we can assume that mu is 0, the mean is 0, and the variance is 1. Just because in the end we do the, here we do the renormalization in any way. So we can start assuming that the mean here is already 0, variance is already 1, so that we don't need to do any normalization. So in that case, this random variables is simply sum of the CI over square root n. Okay. So that is one thing. And another thing that we can assume is the random variables are bounded. And we go from this to the general case by the standard truncation technique. I think that's enough for the simplifications. And now we're ready for the next step. What is the linear works? Sorry. What is the Lindenberg technique? So we want to show something like this. X1 plus up to xn divided by square root n. Now that converges to expectation f of z, where z is the standard Gaussian. Actually, we're going to use this observation. What is one of the nicest property about standard Gaussian? Now, if we look at y1 up to yn, these are independent standard Gaussian. Then if you look at the sum y1 up to yn divided by square root n, this is still standard Gaussian. In other words, we can try to show this discrepancy y1 up to yn divided by square root n. If we can show that this converges to 0, then we're good, because this is simply the same as this one, because we have just seen that this sum of the yi's divided by square root n has the same distribution as the z. So all we need to do is to show that the difference converges to 0. And how do we do that? Assuming that we just have 2, so x1 plus x2 divided by root 2 minus expectation f y1 y2 divided by root 2. The link number swapping method would do something like this. So we'll just swap one random variable at a time. So x1 plus x2 divided by root 2 minus f of y1 plus x2. So we swap the first random variable. And then, of course, we have to add it back. Now it's time to swap the second random variable. So y1 plus y2 divided by root 2. Okay. So this is one term, and this is another term. In here, we swap x1 and y1. In here, we swap, x2 and y2. Okay. And of course, we can do the same thing for n random variables. So the expectation f x1 up to xn divided by square root n minus expectation f y1 up to yn divided by square root n is simply the sum f of, so assume that we already swap up to yk minus 1, and we still have xk up to xn divided by root n, and expectation of the same thing y1 up to yk minus 1. And now it's time to swap the xk, and then here still xk plus 1 up to xn divided by root n. Okay, so it's just a sum k from 1 to n like this, okay, n of them. And for each of them, they only differ in one component. Okay, I sort of run out of space, so let me delete this part and illustrate how to do this part. So let me call the rest of this here A. So basically we have, for each term here, we have expectation F, A, plus xk divided by root n minus expectation F, A, plus yk divided by n and square root n, where a is the common term. Okay, and we use Taylor expansion here around a. So we keep the expectation outside. Here we have fa for the first term, and then the for the derivative we have f prime of a plus the second order term 2n f double prime a plus the error term, what is x k cube over 6n to the 3 halves, and big O of the norm of f triple prime, the infinity norm. So that is for the first term, and the second term is the same. Let me erase this too so that I have space. I use more space than I had thought. Okay, so the second term is going to be the same, right? It's except that, let me write down. Here, instead of xk, we have yk, f prime a, yk square 2n. And there's a big O because it's just an error term. It's not precise, right? Now there are a lot of cancellation happening here. So these go away. Now expectation of xk is going to be 0. So this term is going away. This also go away. Now expectation of xk square is 1. What is the same as expectation of yk square. So this term cancel out with this term. So finally, we only keep have the remaining term, we know that this is bigger of 1 because f has bounded derivatives. And we know that this one is also bounded because of the simplification step where we can already assume that the xk are bounded. So all of that will give us just 1 over n to the 3 halves. Big O of 1 over n to the 3 halves. So in other words, if we add up, so if we, you remember that we do the swapping. Oh, I already erased it. The swapping, so there are k steps because we need to swap k times in order to swap all of the xk to the yk, and each of them has an order n to the 3 halves. So in sum, it is still of order n to the 1 over square root n, what is little of 1, meaning which converges to 0, and what is precisely what we need to prove. Okay. So that takes a long time to prove the central limit theorem, but I hope that it gives you some motivation and because it's also very important for the rest of the talk. So that is the central limit theorem, and again is one of the basic, the simplest form of universality. Now we move on to talking about random functions, and what I mean by random function, it is a combination of deterministic functions, and in this talk we will restrict ourselves to these guys being ak. So here is a1 and here is okay, so here these guys are just some a x to the k, so some monomial for this talk. And here's an example where the random variables are just the random signs. So for this talk, really just keep in mind this toy example when the random polynomial is you just choose the coefficient as a random sign, so either plus or minus 1, and then the question is, for example, on average, how many real roots does it have? And the next question would be, what about the variance, and then what about the distribution of the roots of this one? And this kind of model has been studied since the 1930s, and it appears in quantum chaotic dynamics, and it has a close connection with zero crossing properties of diffusion equations, which some of you here may be more of an expert than I am. And it is also applied to study the so-called persistent probability, because it is very related to the persistent probability of physical systems, which I have no idea about. And it has application in number theories, following a series of paper by Bourgain and Rudnick, but in 2010s, and it is closely connected to random matrix theory. So here in the slide, you see just a picture that shows, how closely connected they can be through bare eyes. So these two pictures, one is from zero of a random function known as Gaussian entire function, and here is a very classical random matrix ensemble known as the Ginebra ensemble. And so on one hand is a matrix with independent entries, and you look at the eigenvalues, and on the other side we have a random polynomials with independent coefficients, and you look at the zeros. And here's the plot of the zeros, and you see like meaning through eyes, it's really hard to distinguish these two, and they really have like very common properties. For example, if you look at one root, it's very likely not to see another root like right next to it. Like something like this would be very rare, for example. Yeah, even though they have many different properties, they are very, very closely related. And some classical examples of random polynomials are the Cox polynomial, which is the one that you should keep in mind for the rest of the talk. And then the Cox polynomial is a special case of the hyperbolic polynomial. And these are invariant with respect to the isometry of the hyperbolic plane, meaning you apply an isometry on the hyperbolic plane, the distribution of roots remain the same. The Y polynomial, when there is a coefficient in front, and that is 1 over square root I factorial. Oh, I forgot to mention these CI for the rest of the talk are random variables independent with mean 0 and variance 1. So the Y polynomial has this coefficient in front, and the elliptic polynomial has this coefficient in front, and even though they just differ in the the covariance of the CI, the coefficient, these have completely different behaviors. So they all are classical examples, and two more are the random Fourier series. So you look at an example is Pn x is the sum, assuming the random variables are just plus minus 1. So cosine jx plus minus sine jx, for example, and j from 0 to n, for example. The random Fourier series. And more generally, one can look at random orthogonal polynomials in which the deterministic polynomial, so Pn, again, Pnx is the sum of ck pk. So these are little p. This is, let's say, call it p. So these are fixed, and these are orthogonal with respect to a measure mu on the complex plane. And these has some applications in approximation theory.
Oanh ơi, có một bạn tên là Quang Khải Nguyễn Hưng có hỏi câu hỏi là cho em hỏi là random function có ứng dụng được vào time series analysis không?
Câu hỏi rất là hay. Thì mình có biết là cái random polynomial này nó có ứng dụng trong game theory, evolution theory, còn time series thì không biết nữa, cũng có thể là có.
Cho em hỏi kỹ hơn được không chị?
Em hỏi đi.
Thì theo em hiểu nãy giờ chị nói là cái random function là mình sẽ gắn cái biến cộng trừ 1 vào những cái hệ số của cái đa thức. Thì giống như là random form, ví dụ như là time series analysis thì thường là nó sẽ model những cái hiện tượng là nó random vào ngày mai á, ví dụ như ngày mai nó liều tăng hay là giảm mình cũng không biết á. Thì theo chị cho em hỏi rằng là có phải là random function này là nó sẽ có thể ứng dụng vào những cái chuỗi nào mà nó có vẻ nó random thì mình có thể mình tìm cách nào đó mình ứng dụng được, đúng không chị?
Chị cũng không biết nha, tại vì chị cũng không có rành về time series á.
Anh có ý kiến, tức là theo như anh thấy á, là trong cái random PDE, tức là coefficient with random PDE with random coefficients á, là người ta sử dụng cái random polynomials.
Yeah.
Dạ.
Ok, vậy là có một số câu hỏi khác thì mình để đến sau talk của anh mình sẽ bàn tiếp. Mời anh tiếp tục.
Yeah. Okay, so with random polynomials, again, the questions concern the distribution of the roots. And for me particularly, I'm interested in the real roots. I have been interested in the real roots, so I mostly focus on questions concerning the real roots. So here are some pictures. Now, here again, the Cox polynomial, meaning the coefficients are random plus minus one. Again, it really doesn't matter whether it's plus minus one or uniform or any distribution that you are interested in. Here, the plus minus one is just, you know, just so you have some toy examples in mind. And we draw a large number of them, draw the roots on the plan, and this is what we see. Most of the roots will concentrate near the unit circle. And here is a lot nicer picture, a high resolution picture, which looks exactly the same. This is actually not random. This is deterministic. They draw all the roots up to n equals 24. But again, it's a lot of properties are the same. So here, you see most of the roots still concentrate near the unit circle. So, and here, like these regions, actually, for example, they has less roots, and the brighter the color, the more roots there are in around that point. Right. And so if we look at this picture, you can formulate a lot of questions that are actually hard to formulate mathematically. And basically, almost everything is unknown about random polynomials. So maybe you will be the next person to, you know, formulate these questions and answer them. And here is to zoom in around the unit circle. So we see actually a lot of structure here that looks like fractals. So let me go into zoom in here. That fractal area around the real line here looks like a feather, and the other structure that I circled on the previous slide looks like a dragon. It's called a dragon-like structure. Nothing has, as far as I know, nothing has been formulated and proven about this structure. And then another kind of question is, what is actually surprising, if it's the first time we see it, here is 1 and here is -1. You see the holes here and also holes here. What that means is why most of the roots concentrate near the unit circle. There are holes around these points, which I think these are roots of unity. There are holes around these points that has no roots. So this circle means that there are no roots. And here's the hole at 1. And hole at I, which looks completely different. So the question, one of the questions that I could actually answer is, what is the radius of this hole? But I have not been able to give a sharp answer to this one. I mean, even this one is still open, meaning so this is of order 1/n. But even that is open. Conjecture is big theta, meaning this is C/n, and that is still open. Okay, and so the method that we use to answer so far any kind of question that we have with random polynomials is, we try to answer the question for the Gaussian case, which is usually the often the easiest one, because Gaussian is about the nicest distribution that you can think of. It is continuous, absolutely continuous with respect to the Lebesgue measure. It has very nice symmetry properties. It has beautiful formulas and so on. It has a lot of tools from Gaussian processes. So Gaussian is, when the CIs are Gaussian, is about oftentimes the easiest. I actually have not seen any case in any of the question that I asked in which the Gaussian is not the simplest. And then the next step is for any kind of distribution that you're interested in, for example, plus minus one, what is actually about one of the hardest already. Usually when you solve, you're able to solve for plus minus one, you're able to generalize it for much more generality. So in order to reduce to the question that you asked originally for your general distribution, use the universality method to compare it with the Gaussian. And then since you already solved the question for the Gaussian, you have the solution for the general case. And this is the method that was originated by a very beautiful paper by Tao and Wu back in 2014, which can be in turn traced back to their work back in 2000s on random matrix theory. So the method of local universality for random polynomials, how is it different from what does it mean? How is it related to the central limit theorem? Then the local universality is just say something like this. If you are interested in the behavior of roots in a local neighborhood, like a local ball, a small ball, or a small interval on the real line, then you are interested in something like this. For example, you're interested in the mean, some statistics. So f is a smooth function, and these are the roots. So these zeta i's are the roots, the random roots of your polynomials, and you apply the function f. For example, f is the indicator function. Then this will count how many roots in this the region that you're interested in, and taking expectation like what is the mean number of the number of roots in the region. And if you are interested in finding something like this, then you can try to compare it with so this is the identity that you're interested in. In the previous slide, there's just one variable in here, but you can also look at many of them because sometimes you want to learn how the roots inside that ball interacts as well. You don't just care about how many of them, but you want to see how they interact with each other. Then you will be interested in something like this. And the universality phenomenon will say that, okay, if you look at this one coming from the CI, and if you look at the same one coming from the Gaussian, so these are Gaussian, then proving universality means that you show that the discrepancy is small. And using this, you'll be able to answer question like, okay, you look at the real line and ask what is the expectation of the number of real roots. So this is the number of real roots. Then if you can show that that compared to the Gaussian, meaning for the Gaussian, you look at the same thing and do the same computation and show that this is little one. And then you can do this calculation and say that this is 2 over pi log n for the cost polynomial, where you can do the precise calculation and say that it's 2 over pi log n. Then from the universality, you will be able to say that, okay, for the general case, this one is also 2 over pi log n for the cost polynomial. a lot of this is not precise. This is actually a bigger one, but I want to correct that. Anyways, this is just the basic idea of local universality. And I think I have about 5 minutes left. So let me go really quick to the application and very quickly go over the idea of the proof.
Oanh, no worry, we started 5 minutes late, so you can go for 10 more minutes.
Oh, great, thank you. Yeah, so using the method of universality, we have some applications. So firstly, we understand the expectation of the number of real roots. So NN is the number of real roots. It's the number of real roots. Pn, which is our random polynomial, and the variance. And then we able to establish the so-called central limit theorem for the number of real roots. There's something very funny actually. With the expectation of NN, it's actually universal, meaning you start with any of the classical ensemble of polynomials that we have seen in the previous slide, then expectation of NN is universal, meaning you change it to the Gaussian, it is still the same. Expectation, meaning the leading term is still the same. With variance, it's actually different. Variance is not universal. What is universal? What is very surprising, and we prove that the variance is universal by the universality method. What is also very quite interesting, but we're not going to focus on that for the rest of the talk. We'll talk a little bit more about the central limit theorem. So this is actually a very common phenomenon in probability. So you have an object. Here is the number of real roots. It doesn't look anything like a sum, but if you rescale it, like minus the expectation and divide by the standard deviation, it still managed to converge to the Gaussian. And for that, people say that the NN satisfies, the number of real roots satisfies the central limit theorem. Let's see how we prove something like this, the central limit theorem. So that's the result that I proved with my advisor Van Vu, that when the, so we have Pn is the sum of Aj, Cj, x to the j, where the Aj here are deterministic coefficients, and assume that this grows polynomially, meaning Aj is about j to the 10, for example. Then the number of real roots satisfy the central limit theorem. And the idea of the proof is still going through the universality approach, meaning we have a smooth test function here, and we apply it to the number of real roots. Here the tilde is stands for the Gaussian. And we want to show that something like this converges to 0. And then we show that the NN tilde, what is the Gaussian one, satisfies the central limit theorem. And then here it says that asymptotically, the distribution of this guy is the same as the distribution of this guy. And these steps show that this guy asymptotically is Gaussian, and therefore this guy is also Gaussian asymptotically. Let me just talk about the first step, the universality step, and how to reduce it. Actually, we use the Lindenberg swapping method to prove it after a bunch of very technical steps. So firstly, what happened is here's NNR, the number of real roots, and we'll decompose R into appropriately chosen small intervals. So and call it N1, N2, and so on. So N will be just a sum of these. in fact, for the model that we're looking at, most of the roots are on the unit circle, concentrate near the unit circle, and on the real line, most of the roots concentrate around plus and minus 1. So these intervals are actually very near plus and minus 1. You may wondering why before I said that around plus and minus 1 there are no roots, and now I'm saying that most of the roots are near plus minus 1. So 1 here, for example, if we look at the radius 1 over n, there's no roots, but radius a little bit bigger, for example 1 over square root n, for example, then most of the roots are here. Then here's just some standard step to approximate the indicator function by smooth test function. But in any ways, we're interested in something like this, and n is already decomposed into a sum of smaller intervals. And for each smaller intervals, we approximate the indicator function of that small interval by a smooth function. So we end up with something like this. So f is a test function, phi I is also a smooth function, and these zeta i's are the zero of the random polynomial. And one key feature is that this sum here can be written as the integral of the log function. So in other words, we end up with something like this. After a lot of steps, end up being able to reduce our expectation f of NR, meaning just NR, and reduce it to this one here. K is another smooth function and just log of Pn. And we want to show that this thing minus that of the Gaussian. So Pn tutor is the Gaussian, and we want to show that this is little 1, meaning it converges to 0. And another step, step is to get rid of the log, because the log is not smooth. So we get rid of the singularity at 0 so that we can assume that the log is gone, and we have a smooth function k here. This k actually different from that k. Let me call it k prime. Now wanting to show something like this. Now if we look at the Pn again, so it's just a sum of Ci, and here is ai x to the I. Now this is just a sum. It's really a sum. If we look at, if we fix x, then this is really just a sum of independent random variables. And here what we show is really looks like we try to show the central limit theorem. So we have a smooth function applying to a sum of random variables, and we show that it's universal. Really just the central limit theorem. And so from here, we use the linear work swapping method in order to prove it. Maybe that causes a lot of confusion. So please feel free to ask if you have any questions. And I think I will stop here. Thank you so much for your attention.
Thanks a lot, Oanh, for a wonderful talk. Sorry that I'm going also between English and Vietnamese and